Greetings of the day, dear students. In this video, we are going to discuss about one important topic, half wave rectifier. In this video, we will see its waveform, what is the input voltage and what is the output voltage, its circuit diagram and its operation, what are the different modes of operation, and we have to do lot of analysis with respect to the calculation part, how to calculate average or DC output current IDC equals to 0.318 Vm by RL, and also VDC output voltage 0.318 Vm, and also its RMS output current IRMS, which is nothing but zero point 0.5 Im, RMS output voltage VRMS Vm by 2, nothing but 0.5 Vm, and also the efficiency of the rectifier PDC by PAC, which is around 40.6%, right? And also the ripple factor, form factor, peak factor, and finally its summary, and we will discuss one example to calculate different parameters in the half wave rectifier mode, right? This is what we are going to cover in this video, right? Observe, dear students, the word rectifier itself indicates. How do you understand the word rectifier? What it will do? Yeah, it will convert AC to DC. AC is converted to AC. AC waveform is converted to what? DC. It is a rectifier. If it is inverter, DC will be converted to AC. If it is an inverter. Now, using this diode as a half wave rectifier, if you observe the circuit diagram, you are having only one diode which is connected in series with the load resistor RL, right? Now, whatever the input voltage is given, that is to be rectified using with the help of this diode, right? Now coming to its operation during positive half cycle, observe here the input voltage is having a positive half cycle and also a negative half cycle. During positive half cycle, the diode will be under forward bias, so it acts like a switch. It acts like a short circuited path. Some assumptions we will take here. During forward biased mode, RF, its resistance is 0 ohms, and during reverse biased mode, its resistance is infinite ohms. This is the assumption we will take. So during positive half cycle, the diode D1 will be forward bias, and whatever the input voltage is applied, depending upon the transformation ratio, right, of the transformer, the voltage will be available across the load. The current will be flowing through the diode. So observe, there is a conduction only during the positive half cycle within the time period 0 to pi. Now from pi to 2 pi during the negative half cycle, the diode acts like a reverse bias and there won't be any conduction. The current flowing through the load is 0. Again during positive half cycle, again from 2 pi, there will be conduction in the diode. Like this, we can observe that in half wave rectifier, only during positive half cycle, the diode will be under forward biased mode and it will be under conduction and current flows through the load. And during the negative half cycle, it will be under reverse biased mode. No current flows to the diode and no current flows to the load resistor RL, and the current is 0 from pi to 2 pi. Now out of this waveform, what will be the DC component that is to be calculated? Don't think that this entire current Im is a DC value. Out of this value, we are supposed to calculate the DC value. For that sake, we need the mathematical representation of the input waveform, which is sinusoidal in nature here. Now, the mathematical form of a sinusoidal waveform is V of t equals to Vm sin omega t plus phi. Here in this context, the phi is equal to 0. The waveform is getting started at its origin. It is getting started at the origin. Phi equal to 0. So V equals to Vm sin omega t. Here, this Vm represents the peak value. Vm represents what? Peak value. Vm is the peak value, right? Now how do we calculate the average value? average value. Observe, in this waveform only it is existing within the time period 0 to pi, but its total time period is, the time period t is defined as the point of time from where again we will get the same waveform. The common mistake here most of the students may commit is they will think that capital T is equal to pi, but that is wrong. In this figure the capital T is equal to 2 pi, because from 2 pi onwards again the same waveform is getting repeated. Up to there it is to be considered as time period capital T. Right? Now observe DC component. Out of this waveform, how much will be the DC value? How much will be the DC value? That is our point of focus. That is our point of interest. Right? Now the DC value is given by, from mathematical basics we know, for any given waveform if you want its average value, what we have to do, we have to take the integral and divide its value with 1 by t. So 1 by t integral 0 to t I of t dt will give you the average value. Here t is 2 pi, integral 0 to 2 pi I of t dt. But what is the mathematical form of I of t? Im sin omega t. The way we will split the integral within the limits 0 to 2 pi, 0 to 2 pi into two parts. 0 to 2 pi is splitted into 0 to pi is one part, and plus pi to 2 pi, pi to 2 pi is the other part. Right? Within the 0 to pi its magnitude is Im sin omega t, but from pi to 2 pi its magnitude is 0. Right? Now integral of sin omega t minus cos omega t, we have taken out Im is the constant, taken outside. So integral of sin omega t minus cos omega t, upper limit minus lower limit. Upper limit is cos pi, lower limit is cos 0. Cos pi minus 1, minus of minus 1 plus 1, cos 0 1, minus is there. So 1 plus 1 2, Im by pi, Im by pi nothing but 1 by pi, 1 divided by 3.143, 0.318 times Im. Very important. In half-wave rectifier the DC value is 0.318 times Im. For example, if Im equals to 1 ampere, then the DC value out of that 1 amp, the DC value is 0.318 amps. Like that we have to understand. Clear? Now what about the DC value Vm by pi? Vm by pi times forward resistance plus load resistance Rf plus RL. Most of the times if the diode forward resistance is very less compared to the load resistance, then you can neglect the Rf value. Then it is simply Vm by pi times RL. Vm by pi RL, which is equals to 0.318 times Vm by RL. So this is the IDC value. This is the IDC value. Right? Now similarly we will calculate the output voltage. What will be the output voltage? Current flowing, IDC current value into load resistance, because from Ohm's law we know V equal to IR, V equal to IR. Right? Now the DC value of the voltage across the load is equal to the current flowing through the load into load resistance RL. But IDC just now we have derived Im by pi into RL. But what about Im? Vm by pi bracket of Rf plus RL. Now again, if load resistance is very high compared to the diode forward resistance, you can neglect Rf. So it is simply Vm by pi times RL will get cancelled, which is nothing but 0.318 times Vm. So this is the DC value of the voltage, DC output voltage of a half wave rectifier. Now what about RMS value or root of the mean, average value of square, root mean square, root of average value 1 by t of square of the current I square of t. We know I of t value. I of t is what? I of t mathematical form. It is a sinusoidal waveform. I of t is nothing but Im sin of omega t. So I square of t nothing but Im square sin square omega t, root of mean of square of the current. It gives us the RMS value, right? From our trigonometric basics, observe, again we will split this 0 to 2 pi into two parts. One is within the limits 0 to pi, magnitude is there, but pi to 2 pi there is no current, 0. So here the integration is only within the limits 0 to pi, bracket of sin square theta can be written as 1 minus cos 2 theta by 2, 1 minus cos 2 omega 2 by 2 into derivative of with respect to omega t, right? Now this 2 is taken outside, Im square by 4 pi, bracket of integral of 1 with respect to omega t, right? It is simply omega t within the limits 0 to pi, minus integral of cos 2 omega t, nothing but sine of 2 omega t by 2, but the limits are 0 to pi. Take out Im square by 4 pi common, upper limit is pi minus lower limit is 0, minus in the place of omega t you please substitute simply 2 pi, right? Sine of 2 pi by 2 plus sine of 0 by 2, we will get sine of 0 is 0, sine 2 pi is also 0, right? So it is simply pi get cancelled, root over Im square by 4, which is nothing but Im by 2, 1 by 2.5 Im. Very important. The RMS value of a half wave rectifier is 0.5 times Im, 0.5 times Im. Clear? But what about Im? Vm divided by Rf plus RL. Again, if load resistance is very less compared to the forward, if load resistance is very high compared to the forward resistance, we can neglect the value of Rf, right? Yeah. Now what about the RMS value of the output voltage? Once we know the current, it's RMS current into load resistance RL, right? So here Vm by 2 bracket of Rf plus RL into RL. Again, if RL load resistance is very high compared to the forward resistance, now our RMS value will be equals to how much? Vm by 2. Vm by 2. Clear? So four important parameters we have calculated: IDC, VDC, IRMS and VRMS for half wave rectifier. Now observe the rectifier efficiency. Efficiency nothing but output power by input power. Here the output power is DC power, input power is AC power, PDC by PAC. But what about DC power? I square RL, I square R. The current flowing is IDC square into RL. So but IDC just now we have derived Im square by Im by pi. So IDC square will be Im by pi whole square into RL. So this is the DC value. What about AC value? RMS, root mean square value, BRMS. I square R, but the R is RL plus RF. So but RMS we have derived Im by 2. So Im square by 4 bracket of RL plus RF. So dear students, observe with respect to the efficiency, PDC by PAC equal to Im square into RL by pi square whole divided by Im square by 4 bracket of RL plus RF. If you further simplify, 4 by pi square RL by RL plus RF. So if you take out RL common and if you substitute the pi value and 4 by pi square, we will get 0.406 whole divided by 1 plus RF plus RL. So the efficiency in terms of percentage will be 40.6 times into 40.6 into 1 divided by RF plus 1 divided by 1 plus RF by RL. So this is the efficiency of a half wave rectifier. Clear? Right. Similarly, what about the ripple factor? The AC component with respect to the how much AC component is present in the output DC component, its percentage. With respect to the DC, how much AC is present? If you observe, for a half wave rectifier, even though it is converted to the DC, but the AC component is more. AC component is more. It is around gamma equals to 1.21, very high. So RMS value divided by IDC value whole square minus 1 will give you the root over IRMS by IDC whole square minus 1 will give you the ripple factor. So gamma equals to VRMS by VDC whole square minus 1 square root. But RMS value we have derived Im by 2. IDC value Im by pi. If you substitute that, we will get 1.21 is the ripple factor. Very very important derivation is the form factor. RMS value by average value is called form factor. The ratio of IRMS root mean square value divided by average value is defined as form factor. But the ratio of peak value out of this waveform, if this is the waveform, so this value is the peak value Vm. So Vm by 2 of this is the Vm by 2 is the RMS value. RMS value. So at some particular instant of time, if you want, that is called instantaneous value. At some particular instant, V of t, that is called instantaneous value. So and Vm to Vm, this is called peak to peak value. So we are having peak value, peak value, peak to peak value, peak to peak value, RMS value for the same waveform, average value, okay, instantaneous value for the same waveform, but each word is having its own meaning. Instantaneous value at some particular instant of time. Peak value is Vm, peak to peak is 2 Vm, RMS value is Vm by 2, Vm by 2, and average value we got is Vm by pi. What is the average value we got? Vm by pi. Peak to peak value is 2 Vm, peak value is Vm, instantaneous value is at some particular instant. If you want at some particular pi value V of t, right? So dear students, observe what I want to say is form factor equals to the IRMS by average value. IRMS equals to Im by 2 whole divided by average value is Im by pi. We will get pi by 2, which is nothing but 1.5715 is the form factor. Keep in mind this is for half wave rectifier. For full wave rectifier again the values will change, right? Now the peak factor, peak value by RMS value, Vm by 2, it is the 2, the peak factor is 2 for half wave rectifier. Now this is what the summary. Observe, these are all the different parameters we have calculated. IDC or I average is nothing but Im by pi 0.318 Im. VDC or average value Vm by pi 0.318 Vm. IRMS value Im by 2 0.5 Im. VRMS Vm by 2 0.5 Vm. Efficiency eta 40.6 divided by 1 plus RF by RL. Ripple factor 1.21. Form factor 1.57. Peak factor 2. So these are all the summary of a half wave rectifier. What are the drawbacks? The ripple factor is very high, efficiency is very low, 40.6% only, and also the transformer utilization factor is also low. So these are the drawbacks with respect to the half wave rectifier, right? Yeah. So this is the summary with respect to the half wave rectifier. Now let me discuss one example on this topic so that we will understand the calculation part, right? Yeah. A half-wave rectifier diode whose internal resistance is 20 ohm is to supply power to a 100 ohm load from 110 volts source supply. Calculate peak load current, DC load current, AC load current, percentage regulation from no load to full load. Dear students, whatever the problem is given, first please kindly understand the data given and use the proper variable for the numericals given in the problem. That is important. Where most of the students face difficulty is what is the proper variable to be taken for a given data in the problem. If once that point is clear, most of the problems will be easy for you. For example, here he specified the diode internal resistance is 20 ohm. Then at that time, it should strike out to your mind that it is the forward resistance denoted with letter RF. RF equal to 20 ohm, and the load resistance is given. So you should get a thought that it is to be denoted with letter RL. RL equal to 100 ohm. Now the voltage is given, source supply 110 volts is given. If nothing is specified, that voltage indicates the VRMS value. That is not the VM value. That is not the VM value. That is the VRMS value. So indirectly what does it mean? VM by root 2 is equal to 110. If you assume that 110 as VM, then entire problem goes wrong. If nothing is specified, the voltage you have to take by default as RMS value. We have to take it as a RMS value. So VRMS equal to VM by root 2. Now VM value will be how much? VM, for example, in this waveform, if it is a waveform is like this value will be how much? VM now. VM will be how much? VRMS into root 2. VRMS value into root 2. So that will be how much here? 155.56 volts. 156.56 volts is the peak value, positive peak. Negative peak will be minus 156. Peak will be 2 times 155.56. Like that we have to understand. Right? Now VM value equals to 155.56 volt. So from our previous basics, what will be the current flowing through the diode? IM, VM by RF plus RL. Right? VM already known, 155.56 divided by forward resistance is 20, load resistance is 100. So 1.29 amps flows to the load. 1.29 amps flows to the load. If you are having a diode like this, if this is the load resistor RL, now the current flowing through the diode is IM. The value of IM is 1.29, but the DC value IDC will be how much? IDC is IM by pi, 0.41. 0.41 amps is the IDC value. Here you have applied the input voltage, right? Diode, forward bias, halfwave rectifier. Current is flowing through like this. Current IL through the diode, right? Now whatever the DC value IM by pi, IM just now we have calculated 1.29 divided by pi, it is 0.41 amps, right? What about voltage? VM value, VM by pi, 155.56 divided by 3.143, 49.51 volts. What about the full load voltage? VM by pi minus the drop IDC into RF, it is around 41.26 volts. Now what about the regulation? The change in voltage from no load to full load with respect to the full load into 100. At no load the voltage is 49.51 minus at full load 41.56 whole divided by 41.26, it is 19.97%. The change in voltage from no load to full load is very high. That value should be as low as possible. That is the major drawback in the half wave rectifier. The voltage regulation is poor. This value should be low. Even though there is a load or no load, the voltage across the load must be constant. But here there is a change of 19%. 19% change is there in the voltage from no load to full load. Now what about efficiency? 40.6 divided by 1 plus RF by RL. So 40.6 divided by 1 plus RF forward resistance is 20 divided by 100. So 33.83% only. The efficiency is less than 50%. Very poor. Very less efficiency. Right? So these are the important points. So this is what all about the half wave rectifier, dear students. Its a summary is important. please practice the summary and keep in mind all these things are only for half wave rectifier, right? So I request once again, please share this app or application with as many students, classmates, friends, and once you have completed this course, and also please guide your juniors also to download this app application, right? So that it will be helpful to the most of the students. And if any topics are missing as per your syllabus, you can simply keep a message to the WhatsApp number and it will be added. Of course, most of the topics are covered as per your syllabus, right? Thank you.